Hello everyone. In this video we are going to discuss about modeling an electric vehicle dynamometer test using Matlab Simulink. This example shows how to model an electric vehicle dynamometer test. Here the dynamometer test, that is a dyno test, is a device that measures the force, torque and power in your vehicle. More specifically, a dyno test evaluates the measure of torque and rotational speeds, giving a reading that indicates the amount of power in the engine. In this model, this example shows how to model an electrical vehicle dynamometer test. Here, the test environment contains and one asynchronous machine, that is ASSM, and then interior permanent magnet synchronous machine, that is called as IPMSM. This is connected back to back through a mechanical shaft. Both machines are fed by high voltage batteries through controlled three-phase converters here. Here this is that 164 ASM produce the load torque here. The 35 kilowatts IPSM IPMSM is the electric machine under test. Here PMSM is nothing but this block represents a permanent magnet synchronous machine with sinusoidal flux distribution. Here the two groups are there, signal build groups are there. Based on that signal group we can request that is a torque request. Your torque request is a input, and load speed is also set by using this signal builder. Here the control load machines, that is a ASM subsystems, uses a single rate to control the speed of the ASM. The visualization blocks subsystem contains scopes that allows you to see the simulation results. Here the design of EV battery system, that is engine systems, also using this Simulink Simscape fluid toolbox. Here this test environment contains an asynchronous machine and an permanent magnet synchronous machine connected to a back-to-back the mechanical shaft. There is a 164 kilowatts ASM produces the load torque. Here this is a subsystem of control machine under test, that is shortly it stands for IPMSM. This control machine under test subsystem controls the torque of the IPMSM model. This is the task scheduler. This task scheduler scheduling for the controller is implemented as a state flow state machines. Here there are two controls are utilized here. First one is outer loop control and second one is a current loop control. Here this is the PWM generator, then is the measurements units. Then the second subsystem called asynchronous machine, that is ASM control load machines diagram. Here this is a field oriented control block is implemented here. This control load machine subsystem uses a single rate to control the speed of the ASM. Then the next one is the visualization subsystems. This subsystem contains the scopes, lot of scopes, that is a measured rotor mechanical velocity, reference measured estimation and limits of torque and phase currents, and reference and real d-axis current, and DC link voltage, rotor electrical angle, stator DQ voltage, phase modulation waveforms, and also the important one, the stator currents and rotor speed and reference model, that is in represented in RPM. Then shaft torque in shaft torque in nanometer, that is a this type of blocks, that is a dyno test, is a device that measures the force and torque or a power in your vehicle. This is also visualized in these subsystems. This is a signal builder, that is a torque request signal builder. Here itself we can give your own torque values, otherwise you can the signal builder block allows you to create interchangeable groups of piecewise linear signal sources and use them in a model. Here also we can import the data sets. By using the data sets we can build the signal, that is your torque request input. Then the load speed also you can set by using you can quickly switch the signal groups into and out of your model to facilitate testing. Here also you can import the load speed data via Matlab script file or Matlab, that is a .mat data. in the workspace also you can import this data. You can also by using the option import option, you can import the data sets for the signal builder, especially for load speed data. This is the visualization subsystems. It shows the ASSM value. There is it shows the signal statistics and cursor measurements and bi-level measurements, and also we can find peak finder. The yellow lines indicate the stator currents, and the blue lines indicate the stator currents and the second stage. Here the rotor speed and reference model also you can see. It is a final output. The shaft torque is measured in terms of nanometer. Here you can also some other important tools are available here. At the time of practical session we are seeing with the visualization subsystems what all the contents are there. Now you move with the Matlab Simulink model. Here the exact Simulink model is available in our YouTube channel description box. Kindly download it and you can check again, analyze the electric engine dynamometer test performance. Here we will already discuss about what is a torque request, and the next one is a load speed. Here this is a block, there is a signal builder block. You can set it on your own value by using this one. You can move here. You can also set this value. There is a torque request. Here otherwise you can import from file, and after execution you can export the data to workspace or in the form of mat file. It is also possible. Here the export this figure to file or to figure window. Here is the in this manner you can see. Then this file also you can save as the Simulink model. This is the first input block. This is a signal builder block. Then next one is a load speed block. This load speed block signal builder. Here also you can set your own value. These are already default values present in this example. Otherwise you can import from file, or after execution you can also export the data to a space or to a mat file. Also you can save the file in the form of Simulink model or SLX file or MDL file. Then these are two subsystems are implemented here in this example. First one is control machine under test, and second one is a control load machine, that is a asynchronous machine block. Here the high volt batteries are involved here. In this high volt, this block models a battery. If you select infinite for battery charge capacitor parameter, the block models the battery has a series internal resistance and a constant voltage source here. If you select finite for the battery charge capacitor parameter, the blocks models a battery as a series internal resistance plus charge dependent voltage are defined by this equation, that is a V nominal voltage is a product of nominal voltage and state of charge divided by your 1 minus beta of 1 minus state of charge. Here where SOC is nothing but state of charge and V norm is the nominal voltage. Coefficient beta is calculated to satisfy a user defined data point AH1 and V1. Here the opposite side, that is the load side, also the high volt battery and the series capacitor here placed here. Here nominal voltage we can set 775 volt here, internal resistance 0.001, battery capacity charge infinite, here we can choose the same thing. Here in nominal voltage in the source side V norm, you can set the V norm voltage, and 0.1 ohm you can set here. Also dynamic, here no dynamics involved here. You can also specify the variables here. The charges you can set beginning value is 8000 you can set here. Here this IPSM converter, as we discussed, this is one of the IPSM converter unit. This converter unit uses the switching devices as IGBT device. Normally there are several options are available here. The switching device GTO, ideal semiconductor switch, and IGBT, MOSFET, thyristor, and average switch also you can utilize. The IGBT switching device forward voltage is set by 0.8 volt, and on state resistance is 0.001 ohms, and off state conductance is 1 e power minus 5 ohms. The threshold voltage is 0.5 volt. Then in the integral diode, it also has the protection divide with no dynamics and the snubbers. There are RC snubbers is another option. Here there no need of snubber here, so that we can keep it is none model. Then this is my IPMSM 35 kilowatts permanent magnet synchronous machine with sinusoidal flux distribution. Here itself we can, there are some settings, parameter settings options are available here. Here we can choose winding type, that is a Y wound or delta wound. You can choose here. In this example, we can set Y wound and number of poles per P. There is a specified the permanent magnet flux linkage parameterization. We can set specify flux linkage, specify torque constant, specify back EMF constant. As per your requirement, you can choose. Then this is the stator parameterization. Here itself you can specify LD, LQ and L0. In this example, we are using the D axis inductance and the Q axis inductance, that is represented by LD and LQ. Then stator resistance, it shows as RS here. Here zero sequence you can set as exclude or include mode. Here you can exclude mode, you can set here. The same thing on ASSM, that is a 164 kilowatts asynchronous machine. This induction machine is a squirrel gauge rotor parametristic using fundamental parameters. Here itself you can set the apparent power and voltage and rated electrical frequency and number of pole pairs and squirrel gauge. Also you can see it is possible here. Then the load side machine converter block. In this machine converter block also utilized IGBT device. Here the forward voltage set as 0.8 volt and on-state resistance is 0.1. The integral diode. Here also you can choose protection diode with no dynamics. Here also you can choose the snubbers, none. Here this is a subsystem of control machine under test IPSM. Here there are two controls, there outer loop control and current loop control. There's outer loop current control using the PMSM current reference generator and PSM torque estimator blocks are there. Here this is our current control unit. This is a PMSM current controller with pre-control control block. And then this is a PWM generator. It utilizes a three-phase two-level block. This block implements a three-phase two-level PWM waveform generator. Here you can choose the PWM mode as a continuous PWM mode. Then another option is a discontinuous DPWM mode. The continuous PWM using the space vector modulation. Otherwise you can choose SPWM, and that is a sinusoidal PWM. In this model we are using space vector modulation. Then the natural sampling or symmetric sampling, you can choose this mode, sampling mode. Then this is the torque scheduler. This is a torque scheduler block, and the clock pulse is applied in 50 microsecond. That's not, and the first task is 1 millisecond and second one is 100 microseconds. Here this torque regulator is a state flow. It is implemented in state flow Simulink block. This is a measurement unit. The measurement unit is having the pulse of here also the VDC filter is involved. It's a relay. Then now you come for visualization unit. This visualization unit contains the main thing, the stator current and rotor speed and reference RPM and shaft control. Now we can see the result, the output. Also you can see the rotor electrical angle and phase modulated waveforms. Here we need this rotor mechanical velocity. This compiling is going on. After that you can see in this type of output visualization subsystems having. Now we can see also by this example, there is you can generate the reusable code, or you can modify the model parameters. You can see the measured rotor mechanical velocity block. This is a particular one. Then this is a combination of stator current in amperes and rotor speed and shaft RQ is measured here. In the same manner, you can in visualization unit you can see separate phase current diagram and reference and real d-axis current. In this manner we can get the phase currents, and this is the IQ axis, that is a IQ axis, output voltage, reference and real Q axis current, and the DC link voltage. And this one, and next one is a rotor electrical angle. The same thing you can get by using this visualization subsystem blocks. Here in this asynchronous machine block, you can view by using the option. You can see, if you click legend, you will get the legend options. Here is a stator current. What are the blue lines indicates what is the yellow line, what is the brown line indicates the stator current. The parts also you can see. Also you can use measurement tools for trace selections. Here itself you can select the stator current states. Rotor speed state, it takes some more time. Also some measurements is a bi-level measurement and trace cursor measurement, signal statistics also you can find. You can also find the peaks also. For every time it needs a simulation mode. For if you are selecting this trace selection, the rotor speed and reference model, it shows like this. Also another important application for this example, you can also copy the print the figure in the form of generated code. There is a M file code or Matlab figure. After Matlab figure, you can you can mark down the which one is the stator current, which one is the rotor speed, which one is the shaft torque point. Also you can find by using this tool called cursor measurement, signal statistics, and bit level and bi-level measurements. Okay, the thing is going on. Then this is signal statistics. You can find the maximum value and minimum value, what is the peak to peak, and what is our mean, what is our RMS value. Also you can find that is a cursor measurements. It shows the this cursor 1 and 2. Here itself you can move this cursor. You can see what is the value. Here you can see at a particular value what is our delta y, delta t value, and what is the 1 by delta t and delta y by delta t values. You can analyze. This is a cursor 2, this is our cursor 1. You can move like this. You can also note down the time and value for the corresponding values. And the next one is the bi-level measurements. This bi-level measurement, it shows the high and low. These are transition values, amplitude and edges, and rise time and slew rate also you can find here. And next final one in measurement is a peak finder. Here also you can find the peak values. Here you can by using there are in this block you can use in the form of stepping options are available here in this Simulink snapshot possible also there. And you can also generate the you can also vary the style and configuration properties and highlight the Simulink block is also possible with this type of visualization subsystems. Then this is the model, the electric model. This also you can modify the model parameters using the reusable codes. Here itself we can machine parameters, maximum power and maximum torque, and stator d-axis inductance and the q-axis inductance. You can also change and the reusable code also generated by using this example called parameters for electric engine dynamo examples. This example already shows the model and electric vehicle dynamo test. Okay, then the next one, the another important result point, the Explorer simulation result using SSC Explorer. This SSC Explorer is nothing but this SimScape result explorer. This interactive app. By using this SSC Explorer, you can measure each and every node, every point. You can see the waveform. That is, for example, elastic coupling, electrical reference. What are the blocks are available here in this model. you can see at the point of gate driver you can see the 6 pulse multiplexer block, what is the value of GIH, what is the value of GIL. In this manner we can analyze the value, for example HV battery, what is the HV battery charge, what is your inductance, what is your number of cycles present here, HV battery 1, then is a IPSM. Each and every subsystem blocks you can analyze the value, that is a C value, can N value, angular position and phase shifter and mechanical rotational reference model and sensing torque and sensing current also possible here. Yes. Finally the ASSM1 electric engine and dynamometer test, each and every point you can check. It takes some more time to represent this output. This is ASM value, it is angular position. Here is angular position difference and angular torque, and this is a lot of, if you are keeping this model here, plus model I am choosing here. If you are clicking means individual value, individual block, you can see that is a power dissipated and PI 6 pulse and torque and velocity, all the things you can measure. Also by using this interactive app you can generate the reusable code for what is your input values. Also you can save the value in the workspace, and the export setup also there is the export setup. You can set the properties like size, rendering, fonts, lines, all the exporting styles also you can make. If after applying your modification with this figure window, apply to figure, you can export this figure in the form of Matlab figure and the JPEG image and any type of image properties you can save. These are these examples discussed about how to model an electric vehicle dynamometer test. Particularly for this type of devices measures the force, torque and power in the electric vehicle you can use. If you like this video, please hit the like button so that it is reach maximum users. If you are first user, if you are first video viewer in my channel, means kindly subscribe my channel, like, share and comments on my videos. Also here I have provided the Simulink file. Kindly you download the Simulink file with my access, use for academic purpose. Thank you so much.